this class also we will continue on chromatography. The next chromatography is called gel permeation chromatography or size exclusion chromatography. So, it is a very useful technique. We can use it for separating molecules based on their size or molecular weight, or it can also be used as an analytical tool to find out molecular weight of unknown proteins or polymers when you have the data for a set of known polymers or proteins. So, the small molecules will diffuse into pores of the stationary phase, whereas the larger ones cannot. So, the larger ones will come out of the column faster, the small ones will take a little bit time. So, there is inverse proportionality between the size or molecular weight and the elution time, and that is what it happens here. So, as you can see, the big ones and the small proteins are travelling down, and the small ones get entrapped into the small pores. So, the big ones come out, and later on we can elute the small ones out of this column. So, basically if you look at those stationary phase, we have pores here, it is made up of lot of pores. So, the small molecules can nicely enter, whereas the larger ones cannot enter, and so they are very porous of different porosity. So, if you look at a typical gel permeation chromatography or size exclusion chromatography chromatogram as a function of elution volume or elution time, okay, the larger ones or the larger molecular weight comes first, and the smaller ones or the smaller molecular weight comes out last. So, we can easily identify molecules over a wide range of molecular weight. So, it is a very useful technique for doing separation as well as for analytical purposes. So, the stationary phase for lipids is made up of copolymers of styrene and divinyl benzene, whereas if it is a hydrophilic material, you may have a hydrophilic type of polymers. So, for lipids you are having styrene or divinyl benzene with pore size varying from 50 to 500 angstrom. They are of spherical particle 5 to 10 micron. The mobile phase could be tetrahydrofuran, that is THF or dichloromethane or toluene. Then if you have proteins and other biomolecules, you generally use aqueous mobile phase, okay, whereas if you are using synthetic polymers, then you can use solvents. So, the detectors, you have viscometer detector, low angle laser light scattering detector, refractive index detector, UV visible absorbance detector, fluorescence detector, differential refractometer coupled with UV, and so on. So, a wide range of detectors could also be used depending upon the type of polymers or biomolecules you are separating. So, basically if you look at how the molecular weight and the size seem to relate each other, the radius of gyration of a solute molecule, okay, that is the size or shape of a solute molecule, is proportional to the molecular weight raised to the power alpha. Now, this alpha is 1 for rod shaped molecules and 0.5 for flexible coils and about 0.33 for spherical molecules. So, the size is connected to the molecular weight. If it is spherical, then raised to the power 0.33. So, that is the relation between molecular weight and the size or radius of gyration. So, materials used in gel filtration like cross linked dextrans, okay, if you are looking at hydrophilic polymer, agarose, cephalose, polyacrylamide, porous glass gels and so on. Cephadax is stable between pH 4 and 10 and almost 30 degrees. It is unaffected by dilute acids or base, but concentrated acids hydrolyze the glycosidic linkages. Sometimes you add a preservative just like toluene, phenol, chloroform, okay, so that you can soak the gel in wet condition to avoid bacterial growth. So, let us look at a simple problem. Two proteins we have, one protein with a molecular weight of this, another 10 power 5 range, another protein with a molecular weight of this, that is 10 power 4 range. They are eluted through a gel filtration column. The first one gets eluted after 220 ml of these continuous phase collected, the other one comes out at 300 ml. So, determine the molecular weight of another unknown protein when it comes out at 270 ml from the column at the same condition. So, we have the elution volume and the corresponding molecular weight, elution volume and the corresponding molecular weight. So, now we want to calculate the molecular weight of the unknown when we know the elution volume. now the relationship you need to remember, it is not, although it is a proportionality, there will be a logarithm coming in, okay, because you remember the size is directly proportional to molecular weight raised to the power some alpha, right, that is why this log comes in here. So, the elution volume and log of molecular weight are linearly related. So, please remember this, it is not just elution volume and molecular weight, but elution volume and log of molecular weight. So, once you remember that, it becomes very simple. We have a minus term here because as the molecular weight increases, log volume goes down, right, as the molecular weight increases, volume goes down. So, 220 ml you know the molecular weight, 300 ml you know the molecular weight. So, you can calculate A and B from this, and then for the unknown we know the elution volume, we can calculate the molecular weight. So, A and B are calculated. So, when it is 270 ml elution volume, the molecular weight is given like this. So, it is a very powerful technique. We can find out using this type of permeation, gel permeation chromatography, to find out molecular weight of synthetic polymers, proteins and so on actually. So, that way it is a very useful technique in addition to the normal separations which you are looking at. The molecular weight, there are two types of molecular weight, one is called the weight average, other is called the number average. So, basically it is called MW and MN. So, MW is given by the relation summation of Ci Mi divided by Ci. Ci is the concentration of the polymer of molecular weight Mi, okay, and so you multiply Ci Mi and divided by all the concentrations here, okay. So, that will give you the weight average, whereas in the number average instead of Ci you use N, that is number of molecules having that molecular weight Mi. So, you divide by Ni, okay, that is total number. So, this is defined as Mn and that is defined as Mw. So, Mw by Mn is also called the dispersity or spread in the molecular weight dispersion, and it is very useful number to have the dispersity. The dispersion number is 1, that means it is tightly packed molecules of almost same molecular weight. If the dispersity is very large, that means you will have polymer chain length of varying sizes. Okay. Then comes the affinity chromatography. This is based on the principle that every biomolecule recognize another target molecule complementary in shape and size. Okay. It is like a protein ligand, enzyme inhibitor, it is complementing each other, it is like a lock and a key. So, it is used exclusively for proteins and antibodies. Okay. So, we can have antibody antigen, protein ligand or protein inhibitor, and so binding is between a ligand and a protein or enzyme, either one of them is immobilized. So, you can have proteins immobilized to capture certain ligand, specific ligands, or we can immobilize ligands to capture certain proteins of our interest on the stationary phase. Okay. Generally they are connected through covalent bond. Okay. So, we can have the antigen and then we can collect the antibodies and vice versa. So, that is what happens here. So, we have the ligand bound to the stationary phase support material. So, a lot of proteins flow, and the proteins which are very specific to that ligand only binds. So, other proteins travel down, and later on we can change the condition so that the proteins that are adsorbed get desorbed and then comes out. So, changing of condition could be either changing pH or salt concentration or ionic strength or dielectric constant and so on actually. Okay. So, for example, you have the ligand which is connected to the matrix with through a spacer. Why do you need a spacer? If you do not have a spacer, the protein will start interacting with the matrix and it will not have a good binding. So, there is a spacer, then the ligand. So, the protein which is very specific to the ligand only will bind to that ligand. Okay. It is a like a lock and key mechanism here. So, you have affinity ligands, okay, like this, and if you have, as I said, if you have the no spacer, the protein will start interacting with the support and it will not fit nicely, whereas if you have a spacer, protein will fit nicely to the ligand. That is why you need a spacer. So, it can be used for separating active biomolecules from denatured or functionally different forms of biomolecule, isolate pure substance present at very low concentration, to remove specific contaminants. Affinity chromatography is used quite a lot in biopharmaceutical application, where we are interested in very pure product, and it is an expensive technique because the ligand, specific ligand of interest is immobilized on the surface of the stationary phase. So, ligand interacts with the protein through a specific binding of an antigen to antibody, a substrate or an inhibitor to or cofactor to an enzyme, a regulatory protein to a cell surface receptor. So, these each one of them are complementing one another. So, we can have enzyme, substrate, analog, inhibitor, cofactor, antibody, antigen, virus, cell, lectin, polysaccharide, glycoprotein, cell surface receptor, nucleic acid, complementary base sequence, histones, nucleic acid polymerase, nucleic acid binding protein, hormone, vitamin receptor, carrier protein. So, you can have different types complementing each other, one on the stationary phase and another coming out to the continuous phase. More of it, glutathione, glutathione S transferase or GST fusion protein, metal ions going to poly his fusion proteins or native proteins with histidine, tryptophan residues on their surfaces, and so on actually. So, techniques used to disrupt the ligand protein. Once you have done the job, you have isolated, you need to collect it back. So, what do you do? We can change to acidic conditions, pH 2 to 4, generally used for protein and for antibody ligand affinity, increase ionic strength, example as in heparin, use specific eluents including the immobilized ligand. Okay. So, the same ligand we can send it, okay, so that the protein comes out, or an analog in the free solution. So, the analog will go replace the original protein bound to the stationary phase. So, different techniques are followed. For example, so I can change conditions, that is desorption of ligand bound protein by changing conditions, environment. So, the Kd value changes. Okay. So, ideally it should be in the range of 10 power minus 1 to 10 power minus 2 here. So, that they get desorbed. So, we can have affinity ligand in the free form. So, the proteins that are bound on the surface will now bind to the affinity ligand, which will get washed and it will come out of the chromatography. Another approach is we can have an analog protein. Okay. This may have more affinity with the ligand. So, that may replace the original bound protein, which can be again removed by washing. Example, for example, elution of histidine tagged protein from histidine trap chelating by adding imidazole. So, imidazole will replace the histidine tagged protein. So, basically when you are looking at a ligand and a protein, okay, there is a equilibrium constant, dissociation constant. So, ligand plus protein gives you the LP, the complex. The smaller the value of Kd, the stronger is the binding. Okay. So, if good binding can be achieved if you are in this range 10 power minus 4 to 10 power minus 6. Okay. So, if it is greater than 10 power minus 4, this will lead to weak binding, and that means the target molecule may slowly leak as a dilute broad zone during sample loading, and it will get washed actually. So, if it is greater than 10 power minus 4. Okay. Kd values can be modified by changing conditions. Okay. I talked about a lot of conditions. If a ligand binds too strongly to the target, then it may be difficult to elute it out. So, we need to balance between good binding so that there is no leaking. At the same time, we should have enough facility or enough conditions, favorable conditions for it to desorb and come out as a washing. Okay. So, if you have larger than 10 power minus 4 as your Kd value, there could be leakage of target molecule. So, what do we do? Residence time is too short for complete binding. So, it requires higher residence time, or another approach is to inject the sample in small portions, flow the sample, stop the sample, flow the sample, stop the sample. Okay. Another approach is to decrease the solvent flow rate, therefore, your residence time gets increased. Okay. Now, let us look at immunoaffinity chromatography. This is a modification of the affinity chromatography, where you are using antibody columns to purify antigens. That is why it is called immunoaffinity, isolating receptors, enzymes and DNA fragments, removal of toxic components from blood by hemoperfusion, it is a large scale preparation of monoclonal antibodies. Another affinity chromatography, that is called affinity tag or affinity tail. We all must have come across histidine tagged on the protein. Then these tag proteins are purified on matriculators such as nickel, and then later on, once you do that, the affinity tag can there be used to purify a fusion protein. Later the native protein can be recovered by removing this affinity tag using some cleaving protein, using enterokinase like. So, you attach a tag like a histidine tag, and then you use a nickel column to capture that protein, and then you collect it, okay, and then remove the histidine tag. Okay. Ion suppression reverse phase chromatography. I did mention this yesterday. If a protein gets ionized, it will appear more polar. So, it may not work well in a reverse phase, because the reverse phase column is a hydrophobic. So, what do? We need to add some chemical, okay, a pH modifier, so that it does not get ionized. That is why it is called ion suppression. So, when suitable, when stationary matrix is non-polar like a hydrophobic material, and the mobile phase is polar like water or sterolnitrile, but sometimes because the protein starts ionizing, it may appear polar. So, a pH buffer is added to the mobile phase to suppress the ionization. Okay. Then it will look like a reverse phase chromatography or a hydrophobic interaction chromatography. This is an ion suppression. These are modified versions of the basic 4 types of protein, like your gel filtration, affinity, ion chromatography, and hydrophobic interaction or reverse phase chromatography. Okay. So, in this technique, ionizable compounds are kept in their ion suppressed mode, because ionized compounds are highly polar. Okay. So, we can use a buffer and appropriate pH, and once we know the pK value, we can keep it in the suppressed state actually. So, weak acids and bases may be effectively separated under reverse phase conditions. The pK of molecule can be used to determine the correct pH of the buffer. Okay. So, for organic acids such as ethanoic acid, pK is 4.75. So, the pH should be kept below its pK. For organic bases such as trimethylamine, pK is 4.19. So, the pH is adjusted to above this. So, by this modification, weak organic acid, weak organic bases can be suppressed. I mean, can be efficient, the dissociation can be suppressed, thereby we can achieve good separation using a hydrophobic interaction or reverse phase chromatography. Okay, now we looked at quite a lot of theory. Now let us look at certain analytical approaches. So, the chromatography column can be considered as a set of n stages, 1, 2, 3, 4, and each stage is well mixed. It contains a stationary phase solid and a mobile phase liquid through which the solute gets partitioned because of one of those physical principles which we talked about, and then the continuous phase moves to the next stage. So, this almost looks like liquid extraction. Only thing is one of the phases remain constant inside the stage itself. So, there is only movement of only one phase, whereas in liquid extraction you have movement of 2 phases. So, the concentration of the solute will keep changing as it keeps traveling here. So, if you want to do a mass balance of the entire stage, the accumulation in the liquid phase in one stage, accumulation in the adsorbed or the stationary phase in one stage, solute into the stage, solute out of this stage, right. So, this is the total mass balance happens. So, accumulation in liquid, accumulation in adsorbent, solute into the stage, solute out of the stage. So, it ends up with the set with a differential equation like this. This is a differential equation, because Cn minus 1 is the concentration of the solute in the mobile phase entering, Cn is the concentration of the solute in the mobile phase leaving the stage n, Cn is the concentration of the solute in the mobile phase or in the liquid that is inside the stage n, and Qn is the concentration of the solute in the stationary phase in stage n. This is how equal, and epsilon is the porosity or the voidage Okay. So, epsilon is the volume fraction of the liquid. So, 1 minus epsilon Vs is the volume of the solid. So, epsilon into Vs, that is volume of the stage, will be the volume of the liquid. So, Vs is given by total volume of the entire chromatographic column divided by n. So, depending upon what is our n. Generally, we would like to take very large n, so that the derivation or the results are much more accurate. So, one point you need to note is n. So, we could have n varying from 1 to capital N, okay, that is the total number of stages. So, we could have several differential equations moving from C1, C2, C3, C4, C5 and so on actually. Okay. So, this is a set of differential equation. Okay. So, one can solve this if the relationship between the concentration of the solute in the mobile phase, concentration of the solute in the stationary phase are related in a linear fashion. That means, if there is a linear isotherm, then you know Q1 equal to Kcn, that means it can be Q1 equal to Kc1, Q2 equal to Kc2 and so on actually. So, when you do that, the equation becomes manageable, it looks very simple, right. So, this is a set of differential equation, but it looks very nice and clean, and this is valid only when you assume linear isotherm relationship and you assume the k value remains constant in all the stages. That means, Q1 equal to Kc1, Q2 is equal to Kc2 and so on actually. So, initially at time less than 0, there is no solute inside the vessel, right, inside the chromatographic column. So, it will all be 0. So, only at time equal to 0 you are injecting some Cf. Okay. So, when you do that, it is easy to solve, let us not go into it, you will end up with an equation of this form. So, concentration of the solute leaving any stage is given by the concentration of the feed phi raised to the power n minus 1 e minus raised to the power minus n divided by n minus 1 factorial. Okay, you all know what is a factorial, right. Factorial 3 is 3 into 2, factorial 5 is 5 into 4 into 3 into 2, like that. Okay. So, the phi is given like this, where it is a function of n, number of stages, epsilon is the porosity or the void volume, V is the volume of the column, K is your partition coefficient, T is your time. So, that will come here. So, with this equation we can calculate the concentration of the solute leaving any stage as a function of stage as well as a function of time when I inject a sample at t equal to 0 of concentration Cf. Okay. So, you have solved this set of differential equation for linear isotherm. Okay. So, if n is equal to 1, then you will, when I inject a sample, that means if the whole chromatographic column is assumed to be a one single stage, when you inject a sample at time equal to 0, the output will appear like this, output will appear like this, exponentially falling, that is for n equal to 1. So, when I slowly increase the n, when I make n equal to 2 and I inject a sample in the entrance, it will go up the concentration and then it will go down. Okay. As you keep increasing the number of n's, total n, so the concentration will keep going like this, and finally it may end up into a nice looking normal distribution or a Gaussian distribution which will obey this equation. You remember this equation which I taught you in the previous last 2 classes. So, for very large n, very large stage number of stages, it will, the output will appear like a nice looking normal distribution or a Gaussian distribution. Whereas, if n is equal to 1, it will appear as an exponentially decaying concentration. Okay. That is why you need to consider the entire chromatographic column divided into several stages of type n. Okay. So, we have this equation and we have these equations. So, we can relate these 2 equations to get relationship between n is the number of stages, right, a relationship between this and these. Okay. So, when you do that, we find something interesting, sigma square is equal to 1 by n. Please remember standard deviation I said is T naught sigma. Okay. So, we get a relationship between sigma square is equal to 1 by n. So, when I get a chromatographic peak, okay, when I get a chromatographic peak, I can calculate number of stages using the width at the base or width at half maximum, or if I know sigma or if I know the standard deviation and the retention time, I can calculate sigma, and from there I can calculate n, that is number of stages. Okay. So, there are different approaches by which we can calculate n, the number of stages, and I also mentioned that this n is the number of theoretical plates. In the previous class I said why they are calling it as theoretical plates. Okay. Then C0, that is the maximum concentration, the peak reaches is also connected as Cf divided by square root of 2 pi n. Okay. So, there are many relationships are brought in which connects all these parameters. Okay. And then we can say T naught, that is the elution time, is equal to epsilon plus 1 minus epsilon k multiplied by V by Q, and then so C is equal to Cf by square root of 2 pi n exponent minus T by T naught minus 1 whole square by 2 by n. You had a sigma square before, so instead of sigma square we are putting n, and here we had C0, and instead of that we are putting Cf by square root of 2 pi n. Okay. So, you see all these are getting connected with each other. So, we can use these equations to calculate many parameters. We can use it to calculate C0, we can use it to calculate number of stages, we can use it to calculate so many things, even k we can use it to calculate. So, if I inject a sample into a chromatographic column and I know the porosity, I know the volume, I know the flow rate, I know the retention time, from the retention time I can predict or calculate what will be the partition coefficient, that is solute partitioning from the mobile to stationary phase. Okay. So, I can do many things with these equations. So, you need to remember all these equations to do several calculations which we will do as the course of time. Okay. So, let us do a problem, simple problem. You have a chromatographic peak coming out, retention time is 10 minutes, the standard deviation is 0.5 minutes. Now, what is the n? So, it is asking you to calculate n. So, remember standard deviation is equal to T0 sigma, that means retention time into sigma. Okay. So, T0 is given by 10 minutes, standard deviation is 0.5, so sigma is 0.05. So, as you know, there is a relationship sigma square is equal to 1 by n, so n is equal to 400. So, n is the number of stages or number of theoretical plates of that particular chromatographic column, and I also mentioned if n is large we can say the efficiency of separation is large, when n is small efficiency of separation is small. So, if I am comparing two different chromatographic column, all I have to do is I will inject a sample and see the peak, I can look at the retention time, I can look at the base, and from there I can tell calculate what is the number of stages of column 1 and number of stages of column 2, and then I can say this column is more efficient than another column. Okay. So, that sort of calculations we can nicely do using these set of equations. Okay, let us look at another problem. So, the retention time is 85 minutes, width at half the maximum is 5 minutes. Okay. So, calculate the number of theoretical stages. Do you remember the equation which I introduced in the previous class between the width at half and retention time and the number of theoretical plates, right. So, you need to recall that. So, if you recall that, I can for example use, or I can instead of sigma square I can put 1 by n. Okay. So, I have this C by C naught is 0.5 and the retention time is here. Okay. 85 is so from there I can calculate the number of theoretical stages, you understand. Okay. So, yeah, I have this equation, and then instead of sigma square I can put it as 1 by n. So, from there I substitute these terms here and then I calculate the number of stages. Okay. So, it comes out to be 1600. Okay. Okay, you may wonder why I am putting 85 plus 5 by 2 and C by C naught as 0.5. So, why am I doing that? At this place the concentration is 50% of the C naught, right. So, the time at this place will be how much? It will be 85 minutes plus 2.5 minutes, right, because the width at half maximum is 5 minutes. So, if I divide by 2, this will become 2.5, this will become 2.5, and this concentration is exactly half of C naught. So, C by C naught at this place will be 0.5 and the time will be 85 plus 2.5, and that is what I am doing here, 85 plus 2.5, T naught is 85, okay, and instead of sigma square I have put 1 by n, that is why here I have put 0.5, from there I calculate n. Understood? Little bit tricky, but it is not very difficult to work out. Okay. So, we will look at more problems as we go along, because they are very interesting problems and they are very useful for chromatographic purposes. Thank you very much for your time.